Hello, my name is Stefan. I work freelance in Berlin and remote, and today I want to present a project of my own. It's called ez-clang. Ez stands for Echtzeit, which is a German term for something like real time. It's a C++ REPL where the code runs on an embedded device, and the picture you see here is a picture of the device I want to use today for a live demo. Before we start with that, I want to go through a small number of quick facts. It's based on Cling, which is the C++ in-process REPL from CERN. I extended that with out-of-process jitting and cross-compilation, and I added an RPC layer to allow it to talk to the embedded device. There is a binary distribution in a Docker container. You can get it from here. And there is 2 reference implementations for the firmware on the device, and they are open source on GitHub. And with all of that, I have to say, take care, this is a very experimental project, and there is a lot of things that don't actually work. What I want to show now in the demo are the things that will hopefully work. If things fail, please bear with me. Let's switch over here. So we have terminal, and maybe I quit that one more time and connect again. So we have a new connection to the embedded device, and here we have a command prompt where we can execute C++ code. Let's see if it's really C++. So this should work now. Oh no, we have to include standard def. Okay, so clang arrows do work as well. And now we should be able to use that size to define a buffer. And I did not do that, that's true. So yes, now it works. And now we can do it like that. Okay, does the buffer exist? Yeah, it has 8 characters, empty, great. We can do other simple things like this and define a string, let's say, something like that. If we leave out the trailing semicolon, it will dump the expression result directly. And we can use things like memcopy now to copy that string into our buffer, including the terminating 0. And I hope that now we have to include cstring. Okay, that works. And our buffer has the string now. I guess we can also memcopy into the middle of the buffer just for the fun of it and use like terminals, literals, I mean. Something like that. And now the buffer contains, yeah, I think that's 2 very good results here. And with that, we can go on to the next point. Maybe let's empty that again. And maybe you can, if you're not so familiar with embedded development, not all parts of the C standard library are implemented for embedded devices. Like standard out doesn't exist really, so there's no good definition of it. So I provide a own implementation of things like printf, and we can load that here as a header like that. But to get the implementation, and this could be better, but it's the way it is. We have to load the static archive as well into the JIT. And it goes like that, and now we have access to a function called ezprintf, and we can hopefully print the string. That's great. We can also print more complicated things. let's say we want to print something that uses these interesting character codes. You may know it from LLVM, and like that's a pretty complex one already, and okay, works. In order to do more interesting things with the microcontroller, we can load a framework like Arduino, and we do it like that. We have a header, and it gives us definitions like LED built-in. That's the number of the pin that targets this small LED on the microcontroller. And we have definitions for high and low, and we can use that to turn the microcontroller on and off. Once we load the static archive as well, we can use the function digital write. Let's get the address first. So, okay, now it's compiling. Like, it's not really compiling, it's linking the precompiled binaries and transfers the compiled result to the device. It's ready now, and the function has an address, so we can be sure we can use it. Let's bring that together. So right now the LED is on, and when we execute that command, it should turn the LED off. Because of the light, it's maybe not so easy to see, but it is this little thing here, and it should get a little lower now. Yeah, okay, that works. We can also turn it on again. Let's see, we have a few minutes left, so let's quickly do a bit more interesting things, like millis is the number of milliseconds that passed since the device was rebooted. We can use that to define a function seconds. And this will, well, dump the number of seconds. Seems to work. With that, we can define something like wait, number of seconds. And we just busy wait until seconds is larger than the end. So, does that work? Wait 1 second? Maybe. Wait 2 seconds? No. Yeah, it's wrong. Okay, there's one problem. I cannot remove yet the definition of wait, so I have to define a new function. And yes, that will hopefully wait for 2 seconds now. Yes, that seems to work. Let's bring that together to do a real Blinky example. Like, the Blinky example is the embedded world version of our Hello World that probably everybody knows. And this is a for loop that will just turn on and off the lamp for 10 times. And this should now blink over here. Yeah. Okay, that works. We can also look how much memory we have left. Okay, 85% from 83 kilobytes in total. Right now, when memory is over, then it's just over. Okay, coming back to the slides, and there is actually an agenda. I want to describe the terminology and the components in the system in the first point, then look at the hardware dimensions, like what microcontrollers are we looking at, go through the REPL pipeline and have a detailed look at the return value extraction afterwards before I will show you where the firmware documentation is and give a short outlook. So what do we have? We have a host computer that I have here with the REPL and everything, and a embedded device that has a custom firmware, and they're connected through a serial connection. The firmware basically implements only the RPC endpoint that we want to talk to. And all the interesting things happen on our host. There is a command line and a Clang frontend, of course, that compiles C++ to bitcode. The bitcode is fed into a JIT backend that's based on argv2 and JIT-link. There is a number of pre-built binaries in the Docker container that we saw, and we need some tools to do the connection. And there's actually bundled firmwares also in the Docker container that you can flash with ez-clang on your controller if you have one. The RPC layer is interesting because it allows us to talk to the device, and it's single-threaded on the device, of course. So all traffic is synchronous, and this is very important because the UART component on the embedded device can be operated without interrupts. So that makes the implementation of the firmware a lot easier, and that's basically the whole philosophy behind the project. We want to do all we can on the host and as little as necessary on the device, so the device can be very simple and slow, because simple and slow usually also means cheap, and that's usually an important property. So hardware dimensions, devices that we're talking about, I want to illustrate that with a comparison to something like a Raspberry Pi that probably everybody knows. The blue circles we see here are the resources on the Raspberry Pi, CPU, RAM, and read-only memory disk, and they are pretty large. So units are usually gigahertz and gigabytes, and if we compare that to the Arduino Due that I used for the live demo, the circles are pretty small because it's more like megahertz and kilobytes that we're talking about. Comparing different microcontrollers to each other, we see the Stellaris LM3 S811 in blue, which is even smaller than the Raspberry Pi, even smaller than the Arduino Due, and the Due in gray. I'm using the Stellaris board in QEMU for testing, because then I don't need a physical device. And the Due is just a good development board that I got used to, so I guess it's possible to use any other development board with a matching processor and instruction set. When we compare this to MicroPython, which is shown here in green, we see that it tends to have a bit more requirements to hardware. And these are the minimal requirements. If we look into the specifications for specific devices, they usually say things like the ESP8266 needs at least 1 megabyte of flash memory, which is a lot more than we have here. And I'm proud to be able to point out that I achieved to compile a ez-clang firmware, a freestanding minimal version, into a 2.4 kilobyte binary. So this is the hardware requirement for ez-clang. And I would say this is something that fits everywhere. A few words for MicroPython. This is a perfectly great project. It's basically a dynamic Python interpreter REPL that runs on the device. So the interpreter is on the device, and it's interpreted on the device as well. And here, I think the biggest difference is really the execution model, because ez-clang is compiled and the toolchain is on the host. I think there is overlapping use cases, but I think the interesting use cases will be those that don't overlap on probably both sides of the range. So I don't think there's really a lot of competition here. The REPL pipeline is the next thing I want to talk about. REPL stands for Read, Evaluate, Print loop. And there's a number of stages that we go through. And this is basically the interesting part, I guess, for toolchain developers. So let's see how it goes. First of all, we compile the input C++ into bitcode using Clang. Here we need device-specific headers and flags and definitions. And we're targeting ARM non-EABI. Clang is embedded into the binary. So this is the way also that Cling works. Once we have the bitcode, we do a number of transformations on that, like promoting declarations to global scope. And one thing I had heavily compared to the Cling implementation is the value reporter. We will have a look on that later on, but for now the important point is that it introduces that edge on the very right that reports the value back from the device to the host. After the transformation, we commit the bitcode module to the org engine as an IR materialization unit, and org will take care of symbol of all the symbol handling. We can just issue a lookup and we'll figure out what code needs to be compiled. It will create an object file, and JIT-link will build a link graph from that and go through a number of link phases, including dead code stripping and symbol resolution. For symbol resolution, we first look up symbols in previous compile units, like previous commands that happened in the REPL. If we have unresolved symbols, we will ask the device firmware if it knows any of those. And last but not least, we will look into static archives that we provided through the REPL through the load command. And there's a few examples for that written here. Once we got that done, we will resolve relocations, finalize segments, and transfer the code to the device and execute it there. And execution will have this embedded part that sends us back the result. And this is the next thing I want to go into detail a bit. Let's say we have this simple expression here. We define a variable a that gets assigned the result of expression 1 plus 2. The result is 3 and it's an integer. And the interesting observation here is that the value 3 is in the memory of the device, and the type information is something that our host knows. So there must be some communication between the two. If we look into the way how Cling does that, it synthesizes a runtime call that eventually invokes print value, and it passes a context object through the JIT code as a void pointer. And because this is all in one call stack, the print value function can just look into the JIT memory and read the value from there. And that's not possible with ez-clang because we have no shared memory. And that's why we have to do it a little different. Instead of synthesizing a runtime call to a print value function directly, we will call this function, which is a built-in firmware function on the device. And it will take care of sending a message back to the host, and we just have to provide the correct values for us. What we also have to do is to register a response handler on the host so that there is someone who takes this message and combines it with the type information for dumping. And in detail, it looks like that. We have this expression. It gets compiled to bitcode. But before that, we have to wrap it into some entity, some function, ez-clang expr 0 here. And clang gives us an AST like this. I stripped it a bit down and removed unnecessary information so that it's readable. So we have a variable declaration A and an initializer with a binary operator inside. And the second step would be to promote the declaration and the initializer to the global scope of the module and replace the use in the function with a reference. The third step is the one I had to modify heavily from the Cling implementation. Here we synthesize the runtime call and pass it a number of arguments. The first argument is the sequence ID number 1. Here we know it at compile time, so we can just insert the immediate value. And the last argument is the size of operation here. It's also a runtime, a compile time constant, so we have no problems here. What we don't know is the address of the future expression result memory. And we also don't know the address of the ez-clang report value function now. So we just insert expressions that will compiled down into relocations that will be resolved from git link in the end, just like every other relocation would be resolved to external dependencies. So in the end, the response handler would catch the RPC message and combine it with the type information, and it can print out the type and the value. And maybe you saw it in the demo, we can also print out the signature of the function because we have rich type information in the JIT. The device firmware is in a very early stage as well, but there is a documentation online. There's one for the RPC interface and one for the runtime interface, and it looks about like this. There is a list of fields that you have to pass through it, and an explanation of the binary encoding that it expects for an example. I hope this is readable and useful. If there's any issues, please let me know, or file bugs, or yeah, I would be very interested in feedback. I think I will skip the Outlook. You can read it on your own in the slides afterwards, and go to my last slide, which shows the command to run ez-clang with QEMU out of the box with Docker, and the second command you can use to connect an actual physical device and run code there. If you're interested in updates to this project, you can subscribe to a mailing list on the website. And with that, I say thank you very much, and I can't wait to hear your questions.
Right, do you have questions? Yes, we have.
So you're compiling code on the fly and sending it to memory on the device, and you're also loading precompiled libraries. I'm wondering, are the libraries precompiled as position-independent code, or how do you arrange the loading for all the code that you're adding that you can't know exactly what you're going to load when?
So I have a little problem understanding the question, but your question is, I compile the code from the REPL from source to binary, and for static libraries, I have precompiled code, and how would that be handled?
Yes.
Okay. So answer one, yes, it's the complete compile pipeline in case of the commands. And for static libraries, I actually have a library tree per device, and they will be pre-compiled with the exact same commands that I use in the REPL, and they will be ready to go for the specific device. That means if you add a new device in the future, I will publish an API for that. You have to pre-compile the libraries that should be shipped with the REPL as well, so that they are compatible with the REPL. It's a very good question, because it also, an issue is debug versus release, for example. If you have an API difference between debug and release, you may run into trouble because you need to go for one, and if it's not compatible, then that's a problem.
Any other questions? No? The moderator picks himself. So question is the implementation of the whole JIT, like the client side more or less, is that open source? Because I think you only list like GitHub links for the runtime on the device.
Yes, yeah. Good question. The point is, it's not yet open source. It's only really the firmwares that are open source. This is currently a spare time project for me, and I don't really find the time to polish it and get it good enough for open sourcing. And of course, I want to find some funding at some point. And I think once that is done, it would be great to get a deal to get it open source as soon as possible. Until then, my plan is to factor out some parts of the binary. So like the command line is no core part of the project. I will make an API for that and allow people to connect their own command lines. And I think the same is true for the compiler, like for the compiler front end and many other things. So the binary size of the closed source part will hopefully shrink down very fast. And by the way, I also want to adopt Clang REPL at some point, which is an upstream project that the Cling developers are pushing forward. And it will be a replacement for the core transaction handling, I think, at some point.
All right, thank you. Any other questions? If not, then thanks for the talk.